So, I guess we meant to start now. Ebuka, I don't know. Can you hear me? Okay, so someone just mentioned in chat that they'd like to see if you can send the link to the GitHub files you shared last week. So you could do that maybe after your presentation. Okay.
Okay, got that.
Okay. So
Yeah.
I'm guessing you're gonna
Uh,
take it over right now. Let me take you back steps so you can take the front seat.
all right. Thank you, fine. Okay. So good day, everyone. Glad to have you guys here once again. I'm sorry, let me close all of my Chrome tabs and we'll kick off. Whatever I'm not using. Okay. Good day, everyone. That's glad to be back here again. For those that have see we see your haircut, Ebuka. Oh, thank you. Yeah, thank you. I mean, the boot camp has been really demanding, so this weekend was the first time I had the chance to do anything outside of the boot camp and work. So yeah, thanks, Pascal. All right, so yeah, last week we did LangChain and um went over LangChain twice because the first one didn't go so well, and the second one I believe was better. And yeah, it was great. We covered everything from, so I'm doing this for those that that may have missed last class. So we covered everything from LangChain introduction down to chunking, output parsers. We got into indexing, vector stores, embeddings, and all of that. I remember the towards the end we were not so able to cover like the ending part. I think that was vector stores, and what I did was I uploaded. So I did a recording and so I attached it to the recording. So I did the recording on my script on my laptop, and then I attached it to the recording of the class. So if you've not checked that out, you can go on our YouTube channel and you'd see that. So the ending parts that's on vector embeddings and vector stores that we kind of rushed, I did the recording and I went in details on on that one. So yeah. Well, today we are going to be progressing, and let me start by sharing my screen. If I please confirm that I'm audible enough. Verifying.
Yes, you are.
All right, thank you. So let me start by sharing my screen. Give me a minute. Let me. I think I should have host controls and okay. Hello, if are you there? Could you help me disable annotation? And let me start
So,
sharing.
what did you say?
So I was asking if you could also make me a host and then also disable annotation.
Okay.
Are you there? If I okay. All right. So yeah, I guess I'm a host now. Please help me with disabling annotation as well. All right. So today we're going to be covering a very interesting topic. Um, and that topic would be retrieval and ranking. So it's I tagged it, this is level 4, the quest. So what's the idea of the quest is, the quest for searching, good documents, the quest for searching those. So we did indexing, we've covered all of that. We've covered how to use the architect, which is LangChain, and we've covered how to, index our data, store them, first of all, converting our data for chunking our documents, then converting them into chunks, and then from converting them those into chunks, pushing them into the vector database. And now what we are going to do is how do we get the right chunk that we need for our query, for our user's query? So that's what Retrieval is about. Retrieval and then ranking, when I get there, I'll explain better. All right, let me start. So yeah, Retrieval overview here. Root retrieval in RAG is the process of intelligently fetching the most relevant pieces of information from your external knowledge base, that is our vector store or other data sources based on a user's query. So when a user asks a question about the data, let's say your RAG system, the document you fed it was, let's say your company's data, something about your company, and how it asks something like, okay, what is the refund policy at your company? How do we optimize our AI applications so that we can retrieve the relevant chunk to that question? So that's what Retrieval is all about. What is it? What is it? It is the search process within RAG. So it's how we do our search. It's just, think about you doing a Google search. That's what Retrieval is. Then the input is the user's query. So my question, your user's question. Then what happens? The action, it fetches relevant data. It refreshes relevant data chunks from your index knowledge base. For example, your vector store. And then we have the output. So what is the output? It's a set of context documents that are passed to the LLM. So the output is not what your user is going to feed. So I don't want us to get it wrong. It's not the response that your application is going to feed. It's going to give your user. It is what the output is the context, relevant context that your LLM is now going to use to augment its generation. So we are in the retrieval part of the augmented generation. So is this retrieval that helps the generation to be augmented, so giving it, in essence, a better generation. So what's the purpose? To ground the LLM in facts and provide it with specific knowledge needed to this thing is too down on my screen. Needed to answer the user's question accurately. This thing right up here. Okay. All right. Why is retrieval critical for AI application? I can't see why is this coming up. Why is retrieval critical for AI application? The knowledge cutoff problem. So we all know about ChatGPT, or that, let me not use just ChatGPT because they've kind of like made a way around it. So your general application, Gen AI, even ChatGPT, they have a knowledge cutoff. If you ask ChatGPT, where was your data last trained on, it's going to tell you, I think April 2025 or whenever it was cut off. So Retrieval helps us. It gives ChatGPT that relevant updated knowledge. So if what it was trained on is data from whenever till April 2025, what happens? We are in August now. What happens to June May, June, July, now August. What happens to all of that data? And you might have experienced it when you ask ChatGPT a question about something that is very recent. You see it goes and do searching the web type of thing. So that's the retrieval part of ChatGPT. That's what retrieval is like. So the hallucination problem. So retrieval is the anchor to reality. So it's what grounds your LLM. So we know the general hallucination that we get from LLMs. It grounds your LLM's response because now you are giving it, see, this is the answer to this question this person is asking, or this document has the answers to the query. Just generate a response using this as context. Get me? All right, then the specificity and accuracy problem. So Retrieval provides domain specific precision. So it's just use the example that I explained about your company document, and they're asking a question about user policy and all of that. So it's domain specific. Retrieval helps that. Another one is transparency and trust. Retrieval enables transparency by citing the retrieved sources. So if you remember that app I demoed, that RAG application I demoed, or even not minus that, when you chat with ChatGPT, when it generates an answer for you, sometimes you see some links. So it's because of retrieval, it's citing where it's got, it's being transparent about what it's used to generate an answer for you. And the cost and efficiency problems. LLMs operate on tokens. Sending massive irrelevant documents into the LLM's context window is not only expensive but also counterproductive, because you're kind of like, allowing it to focus on things, context that it doesn't need. Do you understand? So you're asking, what is the refund policy for when I purchase an electronic gadget at your company? And then the context you're feeding into the LLM is refund policy for, say, plastic gadgets or whatever. It's not necessary. So Retrieval helps us, reduce, because all of this will still be fed into the LLMs, and everything will be converted into tokens. So the more tokens you use, the more you're going to spend, and it's also going to dull your answer. So yeah, I wrote effective retrieval is about signal, not noise, by fetching only the most relevant and concise chunks of text. So yeah, this is a typical RAG workflow. So here we have our documents. We've covered this part where we get our documents, pass them into the embedding model, and then we index them into our vector stores. This was what we covered last week. Now what we're going to do is, so when a user gets a query, that query is passed into the embedding model. We covered that last week as well. And then there's a similarity search that is done in our vector database, and then similar documents are retrieved. So this is the part, this 5 is the part we're going to be focusing on today. Retrieved and sent into the context, into the prompts templates. We covered that last week as well. And all of that is sent into the LLM, and an augmented generation is done. So let's go. So we have different types of search. This particular search, keyword search, I just put it there just to make, just for awareness sake, basically. We don't really use it in RAG, at least the best of my knowledge. So you don't know, when you open a document and then you do Control F or Control Find, and you just type in the words, so that's why it's called exact match. So even if you miss it by a letter, even if you miss one letter, and you won't get that word. So that's keyword search. And it's just that's all I'm going to say about it, because it's not relevant. But I just wanted you guys to know, what it's called, for those that might not, added knowledge. So now, sparse vectors in retrieval. Why sparse? Yeah, we're getting into code. For those that may be wondering, this is not a presentation class. It's like we did last week. Code. So why sparse search still powers the best search engines in the world? Give me a minute. So When you do a Google search, most of what it does is related to sparse vector search. So let's get into what is sparse search actually. We're talking about this. What is it? All right. This down here. So sparse search is based on sparse vectors. It's a way of representing text using exact words. Unlike dense vectors, when I say dense vectors, I was just referring to vector embeddings. We did that last week. So unlike vector embeddings, which represents meaning, sparse vectors represent words directly. So a sparse search, what they are looking for is the exact word, and they're not looking for the meaning. So if you're trying to get if your query is something that needs semantics, so that needs understanding, meaning, that has meaning, you're not going to get it. So one of the places where sparse vectors are used, sparse search is used is when, say for example, in e-commerce sites, exactly, where you want to find like precise stuff. Do you understand? Where you want to find precise stuff, and then you just type in, I'm looking for a iPhone 38 Pro Max and Ultra, and you put that into it, and then all you get is iPhone 38 Pro Max Ultra stuff. That is where that's where we use sparse vectors. All right, let's move on. So, and that's where we use sparse search. So what is a sparse vector? A sparse vector is a vector with one dimension for every unique word in your entire document collection, which can also be referred as your vocabulary. If your collection has 50,000 unique words, each vector is 50,000 dimension long. So remember last week when we were talking about vector embeddings, we talked about how those dense embeddings, their dimensions are 300, and they range from 348 to 1,500 and something, depending. But when it comes to sparse vectors, the dimensions depends, they are not finite, so they depend on the length of your documents, on the how much how big your vocabulary is. So most of the values are zeros. Only the words present in the document have a non-zero value. So the non-zero value is how important that word is in the document. All right. So yeah. So we have sparse vector. So this is an example of what a sparse vector would look like compared to a dense vector, that is vector embedding. You'd see all of these as 0, 0, 0, 0, 0, and then you have 1, and you have 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Why these they are non-zeros, and they usually are used to represent something. These ones, they are used to represent a word. So I'm going to use an illustration now to explain what sparse vectors look like. So take for example, you have a list of ingredients. So you have a list of ingredients you use in your store, let's say your restaurant, and all the ingredients you have, across whatever it is you are cooking. And then you wanted to cook a particular cuisine, or a particular dish, pardon me. You wanted to cook a particular dish, and for that dish, you now take out, how do I put it? You are not going to use the list of ingredients you have, you're not going to use it. So the list of ingredients that you have, you're not going to. Hi, sorry about that. So the list of ingredients that you have, you're going to only use like about 5 of them. You're going to use like 5 of them for that particular dish. So what is the sparse vector? Against the entire so all the entire list of ingredients is what we call your vocabulary. Then that chunk that you're going to use, that chunk of that list chunk that you're going to use for that particular dish is a sparse vector for that particular dish. So you'd say, how many times does how do I put it? So I'm trying to use something. I'm sorry, I should have. I think I put a picture. Okay, I didn't put a picture, but let me use an image. So if I was to calculate this, let's say I want to make something like bread, and what I need is bread, butter, milk, and mayonnaise. And in my list of dishes, what I have is bread, butter, milk, mayonnaise, tomato, pepper, and the list goes on. So if I'm calculating this sparse vector for the ingredients for what is it called, for the bread, because my entire vocabulary, let's say the entire vocabulary is 12 ingredients. Now, out of those 12 ingredients, I'm using 5. Now, when I'm calculating the sparse vector for the ingredients for just bread, it's still going to, the dimension is still going to be 5 because the entire vocabulary is 5. But then when I'm now calculating the one for bread, if I should say pepper, is pepper in let me go back to this image. So let's say this place now, this is the sparse vector for the bread. This place would be 0 because let's say this points represents pepper, the ingredients pepper. But in my table of menu for bread, that is on the grand scale of things. So this 30K is the entire vocabulary, the entire list of ingredients. So, but then now, when I'm now constructing the vectors, the sparse vector for the ingredients for bread, this 0 is going to represent, let's say this position is for pepper, and this place is going to be 0 because in my sparse vector for the ingredients for making a toast bread, pepper is not there, so it's going to be 0. This place could be tomato. This position could be for tomatoes. This place will be 0. This position could be for something else, and it's going to be 0 as well. Now this place that is 1 could be for bread or butter or mayonnaise, and then you give it the number 1 because of its significance. So that's that about sparse vectors. Let me look at how much time I have. All right, I see I've spent a good number of time. Well, sparse vector is always going to take most of our time. So back to my presentation. Right, so how sparse vectors are used. Step 1, you build a vocabulary from all of your documents. That's entire documents. Then step 2, for each document chunk, create a vector. So see the chunks as the the one for bread and all of that and all of that. Then score for each word that appears, 0 for every word that doesn't appear. And step 3, store this in a vector, store those vectors in a search index. All right, now in RAG, we use BM25. It's a very old algorithm. It came out even before all this AI app. I think in the 1990s. I can't remember or early 2000s. But it's a term-weighted it's used for calculating sparse vectors, and it's used for sparse search. Basically, that's the whole idea. We're going to get into the code quickly, but let me give you an overview. So BM25 scores each document based on term frequency. So how often does the word appears in the document? So for example, if the word bread appears more than once in the ingredients, it's going to take like a term frequency of 2 and all that. Inverse document frequency, how rare the word is across all the documents. So if the word is very rare across all of the documents, that means it's very important. And then, I'm going to have to, it's going to get, a higher number or index allocated to it. Then length normalization. So first scoring between long and short documents. So it's just basically saying, take for example, you have a document, since it's keyword that we're searching, you have a document of 200 200 pages, and in that document, the word, let's say the word Kenya is mentioned 20 times. And then you have another document of 20 pages, but the word Kenya is mentioned 10 times. So BM25 is going to normalize, because you kind of, even though this one has more, even though the one of 200 pages has more mentions of Kenya, but when you take it to the grand scheme of things, it's not so relevant. It's not really a keyword like that in that document, because it doesn't appear. So when you take the ratio basically of the both of them, so yeah, that's what sparse vector is about. The strengths of sparse vector is excellent for keyword precision, e.g. coding, product names, and this example of product names, and take for example, you're searching an author in a library and all of that. Is interpretable, you know why a result was returned. It's fast and efficient, no need for no training needed, instant indexing. It's not like what is it called? The business we did last year, and it's perfect for hybrid research. We're going to get into hybrid research as well. All right. The weakness of sparse vector, the overall weakness is it's not good for semantics. So a sparse vector, if you search for joy, if you search for, oh, I am happy in your documents, you won't, where your document has something like, oh, I am joyful, the sparse and BM25 will not be able to like figure it out, because they are two different words. It's not like a vector's embeddings where everything is based on context, based on semantics, based on meaning. All right, yeah. Weakness of sparse vector. Yeah, this should be okay. All right, so let's get into exploring queries. Okay, let's get into the code. Let's get into the code. I think now I need to share my entire screen. I don't know if I'm sharing my entire screen already, but I believe I am. So let me get into this code. So please let me know if can you see Google Colab? Can you guys confirm in the chat that you can see the Google Colab?
Yes, we can see the Google Colab.
All right, thank you. So now let me run this normal lang chain, import my user DB. I'm sorry, I want to make sure that this environment is still active. That because it's going to take a lot for us to get that one up. And yeah, so yeah, it's installing what needs to be installed. So when you want to use the BM25 sparse vector search, what we use is the BM25 package. So it is, you have to pip install rank BM25 and LangChain community. So if I run this code, and now this is like a basic setup. So let's say we have, so yeah, we're going to set up chunks. We're assuming, so this is just a pseudo, just to show you about sparse vectors. So here I'm setting up document, I'm importing the documents class from LangChain core, and I'm setting up, I'm making all of this a list of documents as though they were chunks, basically. So yeah, I said the page contents, the cat on the mat, it was a fluffy cat, setting the metadata and all of that for all of them. Now this is, let me run that code. So yeah, just take it as I have retrieved some documents and then I have chunked them. That's what we did here, basically. That's what we did here. All right, now here we're going to define our retriever. And how do we do that with BM25? From LangChain community, the retriever script imports BM25 retriever. So what do we do next? You initialize the BM25 retriever from our document. So we go BM25 retriever equal to BM25 retriever dots from documents sample chunks. And here we set the K. So K is going to be 2. So that is the number of results that we want back. If I run this code, so this is where I've initialized my BM25 for these chunks. And this is where I have set the number of results I want. So let's do a test. A first test, a query with strong keyword overlap. So the query says fluffy cats. So I'm expecting that this first document, the cat sat on the mat, it was a fluffy cat because there's fluffy cats inside there. So I'm expecting that this first document will be returned. So where are we in this cell? So if I do fluffy cats, and let me even comment out this place so that you guys can see. And then let me separate it. So if I do this, retrieve docs one, so the first document I'm retrieving, bm25.retriever.invoke. Remember, this .invoke is because the bm25 retriever is a runnable. We're importing it from LangChain here. However, it's important that you have to install rank bm25 package separately. All right, so it has the .invoke, that means I can pass it an input. So where is that cell? So where did it go? All right, so if I run that, so the documents, in fact, let me remove all of this fancy talk and let me just show out what was returned. So you see the documents that were returned. So this retriever is just like you pass the .invoke and then you pass your query. So you're sending it to go and search. So if you look, what was returned is the cat on the mat. It was a fluffy cat. You also see another one, a fluffy feline. So fluffy, it took this from this fluffy. So this is one of the advantages of retrieval of BM25. When you want a very direct, exact something, BM25 is sparse vector search is the one for you. Now we're going to use another test query, a query with a specific but rare term. So yeah, the query is Q3 reports. In this place, there is Q3 reports here. So Q3 and reports here. There is Q4 here as well. Let's see what the BM25 will return. So if we run this Q3 report as expected, it returned this because the Q3 is in the query, Q3 is in this document, report is also here as well. Okay. Now let's try a semantic query. So a query where keywords don't match to show you the weakness of your BM25. So yeah, I'm going to pass it a query and say, what do you think about felines? So if you look at in this place, what do you think about felines? Felines are cats and all of that. Oh my God. What's wrong with my mouse? Okay. Can you still see my hand? Sorry, guys. Okay. Let me close my mouse. I think it's the water. What's going on with my mouse? All right. So let's run this query. Anyways. Okay. All right. My mouse is back. So let's run this query anyways. What do you think about felines? Let's see what it gives us. So use this where we see the limitations of BM25. So what do you think about felines? Yeah, we are getting Q4 financial reports show significant growth. The new project reports. Meanwhile, what it's expected to give me back is, stuff like the cat sat on the mat, it was a fluffy cat, or this one, a fluffy feline rested on the rug. So this is where BM25 and sparse vector search fails. When you need things that needs meaning, it doesn't work. So back to our presentation. And now we go, so this is another illustration I have where sparse vector versus dense vector center similarity. So for a bag of words, Sparse vectors are usually referred to as bag of words. So if you see sentence 1 and sentence 2, how old are you, and what is your age, you would see that they have 0% when it comes to sparse vectors. So they have 0% in similarity, but in embedding, they are 91%. Sentence, this other one, how old are you and who's Benje? I think this is German, yeah, or Dutch, yeah, Dutch. So if you check, you see the similarity as well is 0%. And if we're using dense vectors, that's the embedded vectors we covered last week, it will give you about 84%. All right, so let's move into dense vectors. So embeddings, what we covered last week, if you missed it, please revisit the recording. Embeddings are numerical representations of text for semantic search. They capture contextual meaning, improving search relevance and accuracy. So they capture the meaning of what you're trying to say. Okay, what are you trying to ask me? So, for example, in this place where I asked, what do you think about felines? If we were using a vector search, it would have returned the documents we have on cats. Do you understand? Because it knows I'm talking about cats. All right. And I'm not going to cover vector embeddings here because we did that last week and, we've recorded that. And yeah, but you get the whole idea. So this is application of dense vectors. Now we have what we call hybrid search. Hybrid search is the combination of the two. So both dense vector and sparse vector search. So both keyword and vector embeddings. So keyword methods provide a strong foundation for relevant result generation. Dense vector approaches enhance search by understanding and combining both methods achieve optimal balance. And so the combination of the two is going to give you best of both worlds. So for example, you are on a e-commerce site and you're searching for I'm trying to let's say you're searching for an Oxford jeans. I don't know if there's anything like an Oxford jeans. You're searching for an iPhone 38 Pro Max, and what you're looking for is, say, an iPhone 38 Pro Max that has very fast processing, longer battery lifespan than the regular, and you put all of this inside, let's say the AI agent chatbot and all of that. Keyword search would help get results for all of the iPhone 38 Pro Max. Then semantic search is now what is going to filter getting the type that you're looking for, or basically the meaning. You're looking for something that is longer, minimalistic in view, and all of that. That's a minimalistic, so it's not pink or it's not red or any. Say it's something that has like a sleek view, minimalist. So vector search is what is going to help you get that contextual meaning, that semantic meaning, and that is where hybrid search comes in and hybrid search shines. And yeah, benefit of hybrid search. Okay, the benefit of hybrid search is that you get the best of both worlds. So let's just get into the code for the both of them. I do have code for dense vector search, but we've already covered this in our last week. So the code will also be available on our GitHub. Just for us to save time, let's just move on to hybrid search. All right. Oh my God, I have to run this again. Okay. So let me explain what's going on here. So many sessions, manage sessions, thank you. Some sessions, sorry guys. So we just covered the dense vector search, so I think I can go do with that. All right. So, all right, let's run this again. Okay. It's going to take a while, but so in the meantime, let me just explain what's going on. Let me close this. All right. Okay. So while this is installing, the regular, we install LangChain, we install our LLM, LangChain Grok. Sorry if I didn't I know, just realized I didn't make any mention of LangChain Grok. It's the LLM that we're using. It's free. Check our last class recording. You see how to get up and running with it. So yeah, what am I doing? I'm installing. So we're going to be using a different vector database from what we used last time. Let me close this tab. Use this tab. Use this vector stores. So we're going to be using Chroma vector database. Last week we used the Fire's vector store. It's an in-memory vector store. As always, we're going to use sentence transformer. We covered what sentence transformers are, and last week we covered, the use for what is it called, for embeddings. All right. And then rank BM25, since we're going to be using both vector, vector store, and since we're going to be using dense vectors and keyword search in hybrid, we're going to be installing rank BM25. So BM25 basically. And so yeah, why all of that is installing, let's run through the code. So what's going on here? I'm importing the documents, the document class from LangChain core. So you already know that I'm going to be using a pseudo documents chunk. And then Hugging Face embeddings. Yeah, I'm importing Chroma from LangChain community.vector stores. I'm importing the Chroma DB. So you can also persist Chroma DB in your storage. So on your system, you can run it on your system, or you can go to their site and get an API key. And I think ChromaDB are great as well. They're not sponsoring this, but I wish they were. But yeah. So yeah, I'm importing text loader, recursive character splitter for splitting it. And yeah, I'm also importing the BM25 retriever and then Assemble retriever. So while all of this is going, let me cover what Assemble retriever is. So Assemble retriever is what it calls, like it, I think it the English is assembles. So this is what we use to join the two vector stores that we are going to be using. And the two search methods that we're going to be using, or the two search techniques that we're going to be using in our RAG application. So it's the core of the whole hybrid retrieval stuff. And then, okay, this was redundant. And yeah, so here I define the model I want to use. I initialize my embedding model, and so we have sentence transformer. This is the embedding model I'm using, and I'm using, my hands are slippery. Okay, and I'm using, where is that code? So, and I'm using Hugging Face embeddings. I'm using it to download the sentence transformer. That's why it's taking this much time. So it's downloading it basically. So yeah, while that is going on, let me run this code. So here I am initializing the text. I'm creating some dummy documents to highlight, I'm trying to use this as an example. So we have the quick brown fox and all that and all that. And in this place that has run, here I am doing what we did before, just turning them into document chunks, just to mimic document chunks. So now I'm going to prepare those chunk documents. Let's assume that we chunked it from somewhere. I'm going to prepare those chunk documents, and I'm using the recursive character test splitter to chunk them. I'm going to prepare this list of documents. So let's assume this list, and in fact, let me print it. Documents. It should be a list. Your high CPU usage is affecting the quality of the minutes. Let me see how I can go about this. Sometimes, what can I close? Close this time. Hello, Ifeanyi, can you confirm that it's still seeing my screen? I just saw one pop up. Hi, guys.
Yeah, we can still see your screen.
All right, thank you. Okay.
Yeah.
All right, so yeah, so this is a list. So let's take that, this list returning is a PDF document, and each of these items is a page. So here I'm going to chunk them. I'm defining my recursive character text lister. The chunk size is 200, chunk overlap 20. And if I chunk that, I have prepared a total of 8 chunks. And here I'm going to be initializing my vector database. So vector store chroma dots. So using that chroma that we imported here from vector stores. So if I run this, chroma dots from documents, chunks, I'm passing in the chunks. This is the same method we used last week, and I'm passing in the embedding model that I'll be using. One of the things I want to mention in vector when you're dealing with embeddings is make sure you always use the same embedding model for your query, for your input query, and for indexing your documents in your vector store. So I just wanted to say that. Side note. So yeah, I'm using the as retrieval method because it's a vector store from LangChain, and yeah, I'm setting k to 5, which is the number of this thing I want retrieved. So yeah, the vector store has been created. Now I'm going to define my BM25 retrieval. We've covered this, so we have that. Now let's do so a basic hybrid search. So when doing a hybrid search, so I've already covered how we use the ensemble retriever. So this right here is a hybrid search. So what does this ensemble retriever takes in? It takes in a list of the retrievers that you want to use. So the BM25 retriever I have defined and the vector retriever I have defined. Then we also have the weights. It takes in the weights as well. So this weight is what relevance is it going to place on each of the retrievers. So we have 0.5 for the BM25, 0.5 for the vector, and it's an equal stuff. And if we do this, and I use that here, and print out all of the documents. So this is all we get. What is the query again? Okay, info on products WGT 7890. I've already said that. I mean, we've already indexed that. So this is the document that has that. And you see that it gives us, so it gives us this first, and then a couple of other things that might not be relevant to the query, but it gives us what we need first from the index. And okay, all right. So here we are. So what's going on here? Individual retrieval control. Did I run here? Okay. It's the same. Okay. So we are retrieving. So what's going on here is we're retrieving them individually without the ensemble retriever. So this is the normal, results is going to give us if I'm using just the BM25. So you see it has the product stuff at the top. Next, we have how do I change my pin next. For whatever reasons, when I use the vector store alone, that is without the hybrid method, we have the product stuff at the top. And the next context we have is our latest financial report on this. And when the ensemble retrieval gives us a result, we see that in its ranking, it ranked this as the second most important or second most relevant compared to what we got back from the vector store. So this other code, you can run it by yourself. It's just changing the weights between the both of them. So yeah, that's it. Adding more relevance to the vector retriever than to the BM25 retriever. Now, this is not static. You can do it based on what you're building in your application. So if your application is something that is going to do a whole lot of like keyword search, say for like an e-commerce and all of that, maybe you might want to give them equal weights, or you might want to give the BM25 or the keyword retrieval a higher weight. Now let's go get into re-ranking. And yeah, I believe all of this is still running, still intact. I hope I don't have to download any of, oh God. Okay, let me run all of this code. I'm sorry, guys. Let me run all of this code while I'm going through the slides. We can just go through everything that is going on. This should be right. Okay. 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 So I just want to run, sorry about this. I just want to run all of this code. So while I'm going through the slides, whatever that needs to be installed is being installed. Whatever that needs to be downloaded is being downloaded. Okay, back to our slides. So re-ranking. Re-ranking is, what is re-ranking in RAG? So please guys, give me 10 more minutes and we're done. Ranking is the process of reordering a list of retrieved documents or chunks based on how relevant they are to the user's query using a more accurate model after initial retrieval. Why does it matter? It ensures the most relevant documents are ranked at the top. So it ensures that the documents you retrieved are ranked at the top. So like that, I was asking about a product, WTG, blah, blah, blah. Ranking is also to make sure that this particular document that is relevant to this query this person is asking is ranked at the top of all of the list. And it helps the LLM focus on the right context, reducing distraction. So if my hybrid retrieval retrieved, let's say, 10 stuffs and most of it was not relevant, the ranking is what is going to help me like cut all of that down to what is relevant for my LLM. And then it adds semantic depth beyond simple keyword or vector matching. So what is an illustration for a ranking? I decided to use this as an example. Take, for example, you're a chef and you have or you're cooking in the kitchen, and then you have like a junior one that, you send on an errand and all of that. And if you don't have a junior one, if you're a last born, sorry about that. Just think that people are sending you on an errand. You get. In fact, let me use this illustration from last born's perspective. So, take for example, you're the last one. For the last ones in the house, you're the last one. Your elder one sends you on an errand. Go and bring, tomatoes for me to cook, and then in the process of going to bring all of the tomatoes to cook, you do what last ones do, and maybe all of the tomatoes you brought, and maybe all of them are not that great. So, but then they are tomatoes. I mean, your elder one or your aunt or your mom or whoever it is that asked you to get those tomatoes, they need those. They need those tomatoes. They need it. Tomatoes is what they need. But then what you brought, let's say you brought like 10, 12 tomatoes, and then out of those tomatoes, there are some bad tomatoes. I see that I'm cracking. Please, can you guys confirm that I'm still
Yeah, loud and clear.
visible? Okay, loud and clear. All right. Okay, I think it's because of the Jupyter notebooks that are running. Oh, that is not good. But anyways, so now think about this. The retrieval part, you going to bring those tomatoes. Yes, you need those tomatoes. Yes, I need those chunks. Yes, they are relevant. The tomatoes are relevant to what my elder one is cooking. But then they won't use all of those tomatoes. So the hybrid search is the part of me going to bring those tomatoes. Now, where does re-ranking comes in? Re-ranking comes in when my mom or the elder one or whoever it is now looks at the 12 tomatoes you brought, and then they now sort them out, and they be like, oh, out of the 12, they now remove like 6 of them, and then the remaining 5, they're like, oh, I don't need this 5. Maybe it's going to be too much, or it's going to spoil this soup I'm cooking. That is what re-ranking is, and that's what re-ranking is about. That's what it does. It just kind of like refines our RAG process. It refines our retrieval. It kind of like makes our retrieval cleaner, so to speak. So next would be, so why is, get back to, all right, so why is re-ranking critical steps in RAG pipeline? So LLM has a positional bias, so they pay more attention to the start and end of the context window. Important info in the middle might be ignored. So re-ranking is what helps you, what the documents that I've retrieved, I've done a hybrid search, I've done a vector search, I've done a whatever search I may have. Ranking is what helps you like ranks the one that is relevant to the query and puts it at the top, because research has shown that when you give ChatGPT an LLM a context, it's kind of like it pays more attention to the context that are at the top. So the ones that are at the top and then the ones that are at the bottom. So the ones that are in the middle, they will get lost. Another reason for using re-ranking is re-ranking reorders the retrieved documents so that the most relevant ones stay on top. It reduces the noise, it filters out weak matches. So whatever that might have been retrieved and that is not relevant to your query, or that doesn't add too much value to your query, re-ranking is going to filter it out. The another one is it helps minimize hallucination, because it grounds your retrieval. Better grounding is to lead to fewer mistakes, and also reduce token costs. So when you retrieve 10 documents through the hybrid set, and then when you now pass it through the ranking, and the ranker decides that only 4 of these are useful, only 4 of these are needed. That's one of the advantage of ranking. Next slide. Sorry, since my screen is online, I think it's because of the collab that I'm on. Okay, all of this is screen. Sorry about that, guys. Standard, you might not see my screen. Let me open Chrome once again. Yeah. Settings, I can't even. Sorry about that. I'm trying to minimize this. Restore. Okay. This is my presentation. This should be my slides. My backup. I have to run all of this again. Too bad. Let me see if I can put this inside here. So it's just all right, guys. I'm sorry about that. My system just my hand surprised. Just like as well. Okay. I think my 16 gig memory now should have enough juice. All right, so back to where we were. We're at the end. So, so there are 2 stages of retrieval, and we have the retrieval and re-ranking. So let me explain these concepts. So the models, so if I please confirm that you can still see my screen, while move on nonetheless. So the models that we have is we have 2 stages of retrieval. So we have the fast retrieval which uses what we call the bioencoders, and we have the accurate reranking. So that one uses what we call cross encoders. So bioencoders are those embeddings that you see that we've covered in vector search. So what do? They take the query and the documents and they encode them separately. You see how we first of all chunk it, we run them through the embedding model, and then we put it inside, we index it into the vector database, and then when the user gets a query, when the user sends in a query, we also pass that one through that same embedding model we use, and then we take the vector and do a comparison. So that is what bioencoders are. Let me go to the picture. Okay, this is not the image. Okay, whatever. So that's what bioencoders are. They are the embedding models that do take our query and our documents separately, and then it helps us index our documents and then do a quick search for us, our query embeddings against our document embeddings. However, the cross encoders are what we use for re-ranking. What does cross encoders do? Query and documents are inputs together. So the query and documents are a set. You see that when I run the code or when I go through the code, they are the same inputs. They are passed into. I know I have an image for that. Okay, yeah. So this is the bioencoders. Sentence A, you're comparing sentence A against sentence B. So let's say sentence A is our document, sentence B is our query. And then you do a cosine similarity when you embed the both of them. You do a cosine similarity, and then you retrieve the one that is very similar. However, cross encoders, you see sentence A and sentence B, they are entering into the cross encoder together as a set, and then they are being compared, and then there is a classifier that rates the accuracy of the two elements of that set. That's basically what cross encoders does. And this is an image that shows us a stage in our retrieval process. So we have the query inputs, we have the document collection, and you do your initial retrieval, and then you rank your retrieval, and then you send it for content generation. All right, so yeah, I've explained what is on this place. Now let's get into the code. Okay, so oh wow, nice. I think I still have all of this running. If for whatever reason this is failing, but God be praised wherever it is. So yeah, I installed everything I need: LangChain, text splitters, Grok, ChromaDB, Hugging Face, and all of that. I import my environment variable, and this is a demonstration. So when doing re-ranking, what we use is cross encoders. We don't use those embedding models. We use the cross encoders, and so from sentence transformers, I'm importing cross encoders, and I'm downloading a pre-trained cross-encoder model. So this one, it's lightweight, but it is. And if there are so many, if you go to the sentence transformer side, I said you see a lot of cross-encoders that you can use. But this is the one that we're using. So you see, instead of sentence transformer here, what we're doing is cross-encoder. And then you name the name of the model, and then if we go here, let's create a query document pair to score. So we have a query: what is the capital of France? And we have these documents. Paris is the capital of France. The Eiffel Tower is a famous landmark in France. Berlin is the capital of France. France is a country. And then so this is what I was talking about. All right, so we take them as pairs. So both the query and each of the documents, we take them as pairs, the query and each of the documents. So the query against, that's the loop that is going on, that's the list comparison that is going. We are creating a list that has a set of the query and each of these documents. So this is the query. So if I run this, and then I have run sentence pair, so we see this is a list. What is the capital of France? Paris is the capital of France. What is the capital of France? And then what's going to happen is we're going to pass this list through the cross encoder. So so that we can get the score. So here we do reranker underscore model. Where did we define our reranker? So this is where we defined our reranker model. So how do we get the scores? So here we run reranker.predict sentence pairs. So if you run this, that is this list. If you run this, it should return a list of all the scores depending on how they are related, how they score in similarity to our question, to our query. So if I run this and then I print this here, so if you look, the document, so yeah, basically I'm just printing the document and their scores. So if you look, the document that says Paris is the capital of France has a very high score of 8.5. If you see the document that, doesn't talk about, doesn't answer our question, what is the capital of France? Even though there is France inside, there's Paris inside it, it doesn't talk about our question, what is the capital of France? You see, it has a lower score, and the one that doesn't even say anything about, about France has lower score. So that's what Rerankers does basically. So if we had run this through a what's it called now, a RAG application, say we retrieved all of these documents, what Reranker is going to do is going to help us eliminate these documents that have low score, means they are not relevant to our query. It's going to help us eliminate that and then feed this one that has a very high score into our LLM. So that's basically what it is. And here I run that. Yeah, I run that again. I just want to go through this place where I ran. So putting all of this together through a, what's it called again? Sorry. Through a RAG chain. Let's join all of this together through a RAG chain. Yeah, install LangChain community, installed unstructured, and all of these packages needed to use the online PDF loader. So I've installed all of these. Yeah, I'm defining my import. So we're importing from LangChain community loaders, import text loaders. Here we're importing the recursive text splitter, ChromaDB, all of this. And then here we're importing, so from LangChain this time around, we're importing the contextual compression retrieval, and we're importing the cross-encoder reranker and the Hugging Face crossing. This one will help us, download the cross-encoders through Hugging Face. And here we're importing, what we need for our RAG demo, charts prompt templates, the usuals. So yeah, there is this document that talks about Ethiopian culture. We're going to load it from the internet, and I believe this has been run. That's why I'm getting a mark here, and also a number as well. Yeah, so it has been run or ran, whatever the English is. Tasha run. Then we split the documents. That's the next thing that we're doing here. Text split recursive character text splitter, and then we did a chunk size of 1000, chunk overlap of 100. And yeah, this is where we define our text splitter, and this is where we split the documents. Okay. And here we're setting up our Hugging Face embedding model for our vector store. So the embedding model, remember, embedding model is different from the cross encoder. So we use the embedding model to get vector embeddings for our queries and also for our documents so that we can index them. And here we're defining the base retrieval. Here we are initializing our reranker. So Hugging Face cross encoder, you pass in the name of the model that the cross encoder model you want to use. Here I'm using a different one, BAAI and BGE reranker base. And here I'm defining the compressor. So this is basically the reranker. Cross encoder reranker, I'm passing the name of this model that was downloaded, and I'm passing top 3. So it's going to return the top 3 most relevant for us. And here I'm going to create the contextual compression reranker. So what is happening here is this contextual compression retrieval is going to join our base compressor, which is our reranker, which we have defined here. This is our reranker, and it's going to join our base retrieval. thanks, shout out to LangChain. So you do, so this is all you need, it's going to know that, okay, first of all, I'm supposed to use this base retriever, and then from there, it's going to pass it through the compressor. And here I'm defining my query. What does the document say about family in Ethiopia? So it's a document about culture. So if I'm using the base retrieval and I invoke that, these are the documents I'm going to. So sorry guys, I'm not running this live. I don't know what will happen if I run it live, but you can see it has already run. And these are documents I get back. Say family ties remain significant even across vast distances. Ethiopians living abroad are expected to send money to home. That's that. In general, these are other documents. In general, Ethiopians have positive view of US citizens and cultures. Other Ethiopians fondly. I mean, this. So this is what we get when we use our base. So you see, I don't think this is relevant to my query about family in Ethiopia. So let's see what we'll get back when we use our ranker. So we have 10 documents when we use. So now let's use our ranker. So here we use our ranker, and what do we get? Roles and centers of authority. So you see traditional families and religions network cared for the needy, talks about families generally. Okay, you say something about US here again. I'm hoping it also says something about families. Okay, so yes, his family ties remain significant even across vast distances. So it kind of like bottled down all of them. And if you look at in this vector retriever here, we notice that this document, you notice that this family ties remain significant. It was first, but when we pass it through our ranker, it became the third. It became the third. So the thing about ranker is there's the same way there is more than one embeddings, there are more than one ranker. So you try to like play with it depending on your document and depending on what you're doing. See the one that works best for you. That's where evaluation comes in. We'll still cover that in this bootcamp. And then you pass it through your rag chain. Here I define my prompt template, answer the question using only the context below. Context question. Yeah, I'm defining my LLM. I'm defining my rag chain here. And yeah, I'm invoking my rag chain with the query. And what do I get in response? According to the document, this is wrong. Yeah, this was the one I ran before. Let me see if this will break. Okay. You should give me a different answer. So it's generating the answer. I hope it doesn't break. I don't know. I've messed up the query somewhere. Okay, I get what is going on. So I need to run these. Okay. So family ties are significant roles. So let's run this again. It seems nothing will break if I run it. So let's run it again. Yeah, I'm now passing it through the ranker. Let's see what it gives me back as a response. Please don't break, buddy. Don't break, just run. Okay, so these are the three this thing they give me, and then I pass all of that into my rag chain, and when I run this, I should get a relevant answer. Okay, so it's running my rag chain now. Okay, so according to the documents, in Ethiopia, family is important to Ethiopians, and having children is an important part of social life, increasing women's prestige. On average, a woman has 6 children, and all of that. So yeah, that is the purpose of a ranker. The downsides of a ranker is that because you can't do it like the vector embeddings, you know how we first of all chunk our documents, we chunk it ahead of time. Sorry, we embed our documents, our chunks ahead of time and store them in our vector database. And then later when the user comes in to ask a query, we're only embedding the query. The thing about ranker is that it has to like do an embedding and comparison on the go, so on the fly as that query is going. So that is going to add, it's going to do that comparison and computation, between. So if you retrieve 10 documents, it's going to do that across 10 documents. It's going to compute your query and the document one, query and document two, query and do all of that, get the results, and then return the top one. So the downside of Ranker is that it's computationally intensive, and it can also add a little delay because of that extra this thing. But the good side is that you get better RAG, you get cleaner RAG. Yeah, we reduced it from 10 to three relevant stuff for our document, and we passed it down. So see somewhere here that I was talking about gender roles. I was asking about family. No, it said something about gender roles, so that's good. Here it's talking about the outskirts. Here it doesn't mention anything about family. So you see, documents like this are removed. So yeah, that's it on rankers, and thank you all. Sorry that we took another a long time. I'll try and work on making the classes shorter. That's all. Thank you guys. Hello, Raf. Are you there? So someone says Reranker does a better job extracting the right hello, Raf, are you there? If I'm there, I'm coming since my this thing is going to. Okay, I need to join back here. Hi, guys, can you still hear me? If you can still hear me, please let me know. Okay.
Yes, can still hear you.
All right, so somebody says Rerank does a better job extracting the right information, but it can also hallucinate slightly, right? So Reranker is not what does the hallucination, basically. It's your LLM that does the hallucination. So what Reranker does is, after you've retrieved those documents, after a similarity search has been done with your vector search or your sparse search, what Reranker will do is now reduce the documents that are not relevant to your query. So Reranker is just to optimize your retrieval. So there's also a possibility that if what was retrieved is not relevant to the query and Reranker re-ranks it, it's just going to it's going to re-rank the ones that are still, that are similar. So if all of what was retrieved is not relevant to your query, there's really nothing much Reranker can do, because it's going to work on what you retrieved. So yeah. So if your retriever is also bad, if your retriever is poor, Ranker can only pick out the ones that are out of the retriever, pick out the ones that are best, and then send it to the LLM, and then it's left to the LLM to respond. So another way you can now optimize hallucination in a way where retriever is not good enough is through prompt engineering. So we did a class on prompt engineering by instructing your LLM to assess the context that was retrieved. If it is not relevant to the question, you tell it, because you see, for example, when we did that sparse, or was it the dense, the sparse retriever, when we asked about feline, we see that there were all other, I think 3 other documents that were retrieved. Normally, Ranker is supposed to help you with removing all of those. But in the case where all of that is still passing to the LLM, you can instruct your LLM in the prompts template and tell it, if any, ignore whatever, assess, you can tell it, just work with the prompt engineering. Like I told you in that prompt engineering masterclass, prompt engineering, you just have to iterate over it. There's no one formula. But the idea, you have to have the idea for it, for what your prompts. The idea is to tell your LLM that assess this context. If they are not related to the query or to the question, say that you don't know or you don't have sufficient context to it. So that is one way you can, help eliminate hallucination if, the retriever is bad and the ranking is bad as well. All right, so I think that's all. Yeah, someone is talking about the IB search file. Hi, Sir Kalim. I'm going to, so those ones are not on GitHub now. I'm going to upload them to the GitHub. So you can just check the GitHub after this call and you see this will be in our email as well. All right, since there are no questions, I think that will be all. I will close this out. So the link to the GitHub will also be in our email. Yeah, so let me know what you guys think about this. I know I need to work on however, though we'll be having different people now will be teaching. So we have an engineer from Langchain's team. Next week he'll be teaching us monitoring. So next week we're entering the advanced part. On Thursday, we're going to be building our first Naivra project. On Friday, we have another engineer from Langchain giving us a keynote. On Saturday, we also have a VP of AI giving us a what's it called now? Yeah, giving us a paper talk on Saturday. So yeah, Ifeanyi is on the call. Let me leave Ifeanyi to close things out. Thank you. So if you have any more questions, drop them in our Discord. Thank you, guys. Mina and Pascal, please drop your question in the chat, drop it in the Discord. I would answer. We have run out of time. Ifeanyi, can you handle the closing? I see.
Yeah, give me a second.
All right, thanks. Hi, guys. Drop your question in the chat or in the Discord.
Yes, sir. Trying to connect my headphones. Hi everyone. So thank you all for participating in today's session. If you remember what Ibuka said, it's really, really big. We're having two people from Langchain come talk to us. One on Friday is a keynote. As Ibuka said, the vice president of a firm, an AI company, come talk to us on Saturday, and on Monday, not on Tuesday. So that's something we'll show note. There's going to be a little change in the calendar. We're not going to have our class on Tuesday because the Langchain person said that he's not available on Tuesday, but he'll be available on Monday. So we'll keep reiterating this thing for people that are not on the call, or just so that you guys know. Like, I know because everyone has to make time out to participate at this event. It's good if you prepare your questions because it's a different thing when you have the use cases, like where we've gone, where we are at now, and where we'll be tomorrow in the era of agents. People Langchain will probably have like a very good perspective because most people are using their software, if you may call it that, to build agents. So this is me giving you heads up on the kind of questions you should prepare for. Thank you all. I'm very encouraged by the numbers. There are many consistent faces. Shout out to our instructor as always, Ibuka Chukudi. Fantastic. I learned a lot while listening to you. I was like, oh gosh, man, I need to even brush up on my own skills. It's good. Again, I will reiterate. It's good if you post on your LinkedIn, on your Twitter. Post on your LinkedIn and on your Twitter. I cannot overemphasize of this enough. People do check your profile. People do check your journey. Talk about everything. Talk about whatever implementation you have. Yeah. So please, it's really, really exciting. It's really encouraging.